We are presenting to you a domain-specific parallel programming framework for HPC applications. We all are aware about Moore's law and the importance of parallel programming and how parallel programming frameworks help users achieve parallel programming. Let's look at some concerns with existing frameworks. A typical HPC application has its optimizations done alongside with its implementation, and due to this, most frameworks' syntax is complex. From an application engineer's perspective, those are separate fields of expertise where a domain specialist can focus on implementation while an HPC engineer can focus on optimizations. So, an application engineer can focus on their area of expertise if a framework were to separate optimizations from implementations, improving programmability. This separation of optimizations from implementation will also enable the ability to reuse domain-specific optimizations defined. This is because optimizations done regarding a certain domain can probably be used in application made under the same domain due to the use of similar data structures and data access patterns. When a user needs to implement an HPC application, they need to choose a parallel programming framework and hardware that is appropriate to run his application, mainly to achieve their performance requirement. Due to the fact that there are many hardware devices and architectures to support parallelism, there are many frameworks such as OpenMP, OpenCL, CUDA, and SYCL that were introduced to support parallel programming. While some of these frameworks such as CUDA allow parallelism over certain hardware devices only, CPUs, GPUs, and FPGAs by specific manufacturers, some of the frameworks such as OpenCL and SYCL allow parallelism over many hardware devices, given that the framework is supported by the end hardware. So it will be hard to change the framework or hardware once you have chosen it, leading to issues with portability. It is not uncommon for HPC application kernels to have variants. The execution plan is where these variants differ mostly from one another, meaning the optimization part is what actually is varying. So instead of having separate implementations of the same kernel, we can have more portability if we can choose the optimizations at runtime. The portability aspect previously described is important because applications or kernels are usually ported into different frameworks and hardware with the intention of achieving better performance. So, with the portability aspect, users get the ability to avoid performance limitations made by limitations in frameworks or hardware, meaning users will be able to experiment or port to different frameworks or hardware with less effort. Let's look into NOMP's features and what goals are achieved by NOMP with examples. First feature is, NOMP offers simple pragma-based syntax for implementation of your application. As you can see in this example, the NOMP implementation will be closely similar to serial implementation. So the NOMP code will be easier to debug against the serial implementation if anything goes wrong. Also, the NOMP implementation will have a lower number of code lines compared to implementations of other frameworks. As for this example, you can see how NOMP implementation is less complex and easy to read than the OpenCL implementation. This is one way how NOMP achieves better programmability using simple syntax. The second feature is, NOMP separates an application implementation from its optimizations. Let's look at an example where an application engineer and a performance engineer try to implement a simple HPC application using NOMP on the left and CUDA on the right. You can see how an application engineer and performance engineer can specify the kernel transformations separately, while in the CUDA application, both are done together. This also promotes the reusability of the transformations in different applications or kernels in the same domain. This is how NOMP improves programmability by separating optimization from implementation. The third feature of NOMP is just-in-time compilation support for kernels. This allows the optimizations to be defined at a higher level and be applied at runtime rather than being applied in compile time. Since it is not uncommon for an HPC application to have kernel variants, NOMP allows the user to have multiple variants of the same kernel with a single implementation and different transformations specified, rather than having multiple implementations of the same kernel. With this example, you can see how NOMP maintains a single implementation of the kernel, while you have to maintain separate sources for the CUDA implementation. In a performance engineer's perspective, allowing transformations to be specified at a higher level also allows the user to experiment with different transformations with ease to choose between better transformations regarding achieving the HPC application's performance goals. The fourth feature of NOMP is that it supports multiple parallel programming frameworks as backends. This gives users the option to port their implemented backends to another framework such as CUDA, SYCL, OpenCL with less effort. Here, only the specified transformations would have to change. This is the high-level architecture of NOMP. NOMP has two main users, the domain specialist and the HPC engineer. Domain specialist does the implementation of the HPC application, while the HPC engineer specify the optimizations which requires their respective expertise. This is the NOMP source code. As you can see, NOMP uses a pragma-based programming model to annotate C source, with details on which sections of C source must be executed on device side and when to perform data transfers. Now let's talk about the optimization script. We use this script to do domain or kernel-specific transformations at runtime. This is an external Python script that doesn't require any changes in the original C source and can be customized or changed without recompiling the original C source. NOMP has two major components, NOMP compiler, NOMP CC, and NOMP runtime, libnomp. In the compile time, NOMP CC replaces NOMP pragmas with NOMP runtime calls and links them with the NOMP runtime. Libnomp is the loopy-based runtime of NOMP, which can generate and tune device code from the C source at execution time. Loopy is an external Python library that support kernel transformations and back-end specific device code generation. It supports OpenCL, CUDA, and SYCL kernel generation. In order to generate device code, first we have to create a loopy kernel. A loopy kernel is an object that has details of the user-given C kernel. NOMP uses libclang to parse the C source in order to create a loopy kernel. After creating the loopy kernel, NOMP does kernel transformations using a transformations specified in the transformations script. Then, in order to do device code generation, Loopy uses cgen to create a relevant abstract syntax tree. Cgen offers a simple abstract syntax tree for C and related languages to allow structured code generation from using Python. Currently, Loopy uses this method to generate CUDA, OpenCL, and SYCL. Then the generated code will be compiled using a specified compiler or runtime and will be executed on the device. This is a performance comparison graph of a multi-kernel HPC application Lanchas. In green, you can see the performance of the native CUDA implementation of Lanchas, while in blue, you can see the performance of the NOMP CUDA implementation of Lanchas against different standard datasets. You can see how native CUDA and NOMP CUDA both have the same performance, which is our goal. Hope you enjoyed our project demonstration. Please feel free to check out NOMP at github.com/nomp-org. Thank you.